Hello everyone. We are going to start with vector spaces. First of all, we're going to focus more on what is a vector space and a subspace. The topics I'll be covering today are a definition of a vector space, some very specific examples of a vector space, and a subspace of a vector space, and some spanning sets and its relation to subspace. So let's start with the definition of a vector space. Now, a vector space is related to a set, first of all. It's a non-empty set. So I'm going to give you a very simple way of looking at it. I have a set, a non-empty, in which it is some elements or objects, which we call them vectors. Okay, so we have a non-empty set containing some elements, and we define two operations on it, addition and scalar multiplication. And we're looking at scalar multiplication in here for, say, scalars by real numbers. And then in those sets equipped with these two operations, they are subject to some rules, 10 of these rules. If all the objects satisfy these 10 rules, then what we say is that that non-empty set of objects is called a vector space. And the elements, because it is called a vector space, the elements or the objects of that vectors, the set, is called vectors. Okay, so this is kind of similar to the vectors we have been using around, but it actually becomes very, very general. And the vectors, when I say the word, it is basically saying these are elements of a non-empty set which have two operations defined on it, and it satisfies a set of 10 rules or axioms, we call. So let's look at those 10 axioms. The first axiom is that if you're given two elements, u and v, in the vectors, in the set, capital V, and we say if you're given the sum, and this sum which we denote by u plus v is in V. So that means it is basically calling off a closure additive property. Now, the next one, it says it doesn't matter how you add the elements. There's places. It doesn't matter if you say u plus v or v plus u. It's basically the same. This is called the commutative property. Let me write this down. So this is the commutative property. The above one is called the closure additive property. Okay. Now, the third one is when you add three elements, and all these three elements u, v, and w are in that non-empty set V, it is how do you pair and add them up. It does not matter. I can add u and v first and then add a w, or I can add v plus w first and then add a u. So it is the way it is added, it has no effect on the final answer. So this is called the associative property. Now, then we have a zero vector in V, the capital V, such that when I add the zero vector to any vector in the non-empty set V, we get the element back itself. So this zero is called the additive identity. So this zero is the additive identity. Okay, so for every vector u in the capital V, the non-empty set, there is a vector negative u, such that when you add u with negative u, you get the zero vector. So this minus u is called the additive inverse. So we say minus u is additive inverse. Okay, so these first 5 properties, guys, are related to the additive addition operation. Okay, so we call these first 5 the additive axioms. These first 5. Okay, now let's look at the next 5. Now the next 5 are related to the scalar multiplication. Okay, so the first one, you have a scalar. If you multiply any vector u in the capital vector V, that is a non-empty set, by any scalar, and we denote it by Cu. If it is back in V, then this is what we call the scalar multiplication is closed in C. That's what we mean by that. So if, in other words, if you have a scalar multiplied to any vector in the non-empty set capital V, then it is called the scalar. We say the scalar multiplication is closed in V. Capital V, guys, here. Okay, now the 7. When you multiply C to the sum of any 2 terms in the non-empty set capital V, then C can be distributed inside these 2 terms. So it's C times U plus C times V. Or if you have another scalar, say D, so C plus D times this U is the same as CU plus CV. Now this small v is a vector. The capital V, remember, is our empty set. So these 7 and 8 are called the distributive property. Okay, then if you multiply a scalar C with D times U, or you multiply the 2 scalars CD, then you multiply to a vector in the non-empty set, then the final answer is the same. The final thing is when you multiply any vector U in the non-empty set capital V with a 1, you basically get the element itself. So this 1 here is the multiplicative identity. So the last 5 properties, guys, they are related to the scalar multiplication. So these are called, in a nutshell, we call them as scalar multiplicative axioms. Okay, so some observations. The 0 vector in the non-empty set capital V is unique, and this negative U again in the non-empty set V is also unique. Then if the scalars we are taking in this non-empty set, they are real, then the capital V is called the real vector space. And if the scalars are complex, then V is called a complex vector space. Now we are going to look at some very specific examples of vector spaces. And I'll be using them again and again, so I would like you to be very, very much familiar with these specific vector spaces. So the first one, this is the usual R, vector space of n ordered tuples, Rn. So this Rn is called a real vector space on n ordered tuples, where the vector addition and scalar multiplication is defined as given 2 vectors u and small v in Rn and C a scalar, then the vector addition is nothing but adding up the corresponding vector elements of those vectors. So u and v is in Rn. So u is a vector which is an n ordered tuple which basically means is u1, u2, un. So that means this is an n-ordered tuple. Remember, n-ordered means all these elements inside the vector u in Rn, these elements are going to be in a specific place. So I'm making my life simpler. I'm writing it as in a row vector plus v1, v2, vn. So basically we're adding the corresponding terms, u1 with v1, u2 with v2, un with vn. This is the normal vector addition we have learned. The scalar multiplication is when you multiply a scalar to u, you're basically multiplying to every element, every term inside this vector u, which is in Rn. So it is c times u1, c times u2, c times un. If you remember your things when we started in the matrix theory in this class, we said a row vector or a column vector, and depending upon what was my vector space, if it is here it is n, that means there are going to be n elements or n rows or n columns depending upon how we write down the vector. Okay, now we're going to talk about a very special vector which is called an M22. Now this vector M22 is a vector space of all matrices of size 2 by 2. And when we talk about vector addition and scalar multiplication, this is the normal vector addition and scalar multiplication of matrices we have learned. So when we say M22, that means it is all matrices of size 2 by 2. And every time you will be given a vector space, guys, keep in mind, you will be given a vector addition and a scalar multiplication. So M22 is this, where any two vectors in M22, say u and v, are two vectors in a vector space of all matrices of size 2 by 2, then the vectors look different. That is why in the beginning when I said, hey, this is a non-empty set equipped with vectors. Now that vector will not always be the normal vector we are used to. In here, our vectors are not looking like matrices. And you will see further on these vectors may change, the way they look like, the shapes would be different. But they are basically saying, this is an element of this non-empty set. Now, what is my set equipped of? Here, my set is equipped of all matrices of size 2 by 2. So, let's come back and see what the vector addition and scalar multiplication looks like. So, if I say M22, so M22 is like I'm adding two matrices of size 2 by 2. So, I will add the corresponding elements, A11 with B11. That's the element here. Then A12 to B12. That's this element. It's its first row, second column. Then A21 plus B21, and then A22 and B22. Oh, that's a typo, guys. A22. It should be A22. Okay, the scalar multiple is basically multiplying every element inside this matrix with a C. So CA11, CA12, CA21, CA22. Now, we are going to look at a vector space which is very different looking. This vector space is defined as f from the domain is minus infinity to infinity. What basically now we're looking at is a non-empty set equipped with real valued functions defined on the entire real line. This is how we define an entire real line. And that is basically the domain of the function. So we say that f defined on the real line, minus infinity to infinity, is a vector space of all real valued functions where vector addition and scalar multiplication is defined as. So we're given two elements, f and g, in this set of real valued functions and a scalar. Then when we are adding two functions, so we did f plus gx. This is how it is depicted. It's basically you're adding every element fx plus gx. A scalar multiplication, c times f of x. Cf of x. Okay. Let's look at some very important concepts here in this vector space of real valued functions. The zero vector in a real valued functions is nothing but the constant function which takes every element in the domain to a zero zero element here. So thus 0 of x is called the additive identity. What is minus f in the vector space of f from minus infinity to infinity? It is you basically multiply the whole function by a negative number. That is, minus f is minus f of x for every x in the domain of the function. This minus f is called the additive inverse. In this class, I won't be focusing much on it, but I want you guys to be aware of these vector spaces. This f minus infinity to infinity will not be coming that very often. But the next vector space, yes, I'll be talking a lot about that. And this vector space, guys, is a vector space of polynomials. Okay, so let's look at a P sub n. It is a set of all polynomials of degree at most n. We call this as a vector space where the definition of addition and scalar multiplication is given below. So let's write what does a vector px, element of this polynomials look like. It is a0 plus a1x because it is of degree at most n, a2x2 plus dot 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 plus anx n. And a qx, another polynomial defined at b0 plus b1x plus b2x squared. Oh, there's another positive guys missing. Dot 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 plus bn xn. These are elements in Pn, where all these elements a0, a1 to an, b0, b1 to bn, these are real numbers, and c is a scalar. Then when we add the vector addition, basically we're adding the like terms. If you remember that when you add polynomials long time ago, guys, very long time ago. So we're adding a constant a0 to b0. That's the element here. Then adding the elements a1 plus b1, which have x as their component next to it. Then a2 plus b2 x squared plus dot 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 plus an plus bn x to the power n. A scalar multiple is basically you multiplying a constant c to every element, to every term, sorry, not element here, every term inside this polynomial p of x, c of a0 plus c of a1x plus c of a2 x squared dot 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 c of an xn. Now this Pn, the set of all polynomials, is very, very valuable and applicable in statistical trend analysis of data. So if you are having to do some statistics and it's relating to some analysis of trend analysis, Pn would be, this vector space will come very, very handy. Okay, now I would like to talk about how do you prove that something is a vector space. Now, in order to prove that something is a vector space, we have to know the vector addition and the scalar multiplication defined on that vector space. And after that, what we need to do is we have to prove all the 10 axioms. Yes, I agree, it's a lot of work, but I want you to be aware of it. So what I've done is I've written down in detail one of the examples to prove that Pn is a vector space. And I have uploaded it on D12 for you guys. Okay, so I would like you to, I'm going to show it to you what it looks like. Okay, so as I said that I'm going to show you an example where Pn is a vector space and it will prove all the 10 axioms. It has been uploaded for you guys, but I'm just going to quickly go over it. So you have an idea that when we are proving something is a vector space, there's a tons of writing for it. Okay, so if I have to prove that Pn, a vector space of polynomials of at most degree n, is a vector space, okay? So what you're going to do is we're going to take 3 elements, p, q, s. These are 3 polynomials in P sub n. And I'm going to take 2 scalars, alpha and beta. So first thing I have to prove is if I take 2 elements and add in Pn, it actually is again in Pn. And by the virtue of the definition, you would notice that Pn is closed under vector addition. Clearly, if you notice, you just basically have to write these elements. It's exactly what it was given in the lecture notes. Okay, then then the second property we have to prove is that it is commutative. Commutative means it doesn't matter which one b is written, the polynomial is b is written first or the polynomial q is written first. It does not matter. In the end, it is the same. So P plus QT is PT plus QT is the same as QT plus PT. It's just basically, if you notice, these are coefficients of the variable T. So an plus bn tn is the same as bn plus an, because these are real numbers, guys. It doesn't matter which one you put first. Okay, then the associative property. In other words, if I have three polynomials, p plus q, and then I add an s to it, it's the same as I'm adding q and s first and then adding a p. It's all based on the polynomial additions, guys. So the polynomial addition is associative. You can just look at all these things. Okay, it's just basically writing a lot. Okay, then we have to prove what is the additive element, what is the zero element. A zero in a polynomial is of zero element, which all the coefficients of the variable t is all 0, 0, 0, 0. So when you add a zero vector of a polynomial to any other vector p, you get the vector p. Okay, p plus 0 is the same as 0 plus p. Okay, so then we look at what is the negative. So if I have an element p in a polynomial, then is there a negative p? Yes, there is a negative p too. And that is, I'm going to be making my life, so I say, hey, let this be r of t. And then when I add, so p plus r of t is p minus of pt, which basically means an minus an times t to the power, that's the variable of the polynomial, tn. It's a polynomial of degree tn, plus dot dot dot, a1 minus a1 t plus a naught minus a naught. So everything is a 0, 0, 0. We get the zero vector, which is coming from here. Okay, now these were the all 5 additive elements. Now we're going to look at the scalar 5 axioms. So if you multiply an alpha, a scalar, to any polynomial, basically you're multiplying normal, scalar multiplication to any polynomials. That means alpha times an plus alpha times an minus 1, t to the power n minus 1, guys, here, plus alpha a1t plus alpha a naught. It is an element again of a polynomial. Okay, so Pn is closed under scalar multiplication. Now we're going to look at those distributive properties. That means alpha times p plus q of t. That means I have an alpha which multiplying to the sum of 2 polynomials, which is basically you multiply alpha to individual polynomials and it is going to give us the same answer. So it's just basically playing with these. It's a very, very just plain writing down. So alpha times an plus bn is the same as you can individually take alpha inside, an plus alpha times bn, tn, and then you can separate just using normal algebraic things we have learned long time ago. Okay, another way to look at these distributive properties is that if I have 2 scalars, alpha and beta, and I multiply it to a polynomial p of t. So basically it means you can alpha times bt plus beta times b of t. It's still the same. Okay, then the second last property of the axiom is basically that you're multiplying alpha. So if you have a polynomial, 2 polynomials, say alpha and beta, you multiply beta to p and then you multiply alpha to it. Again, you will get the same answer as you multiply these 2 scalars together and multiply it to a polynomial. And the final one is what is the multiplicative identity of a polynomial p of n. Then you just simply, it is 1. 1 is the multiplicative identity. So basically we have proved all the 10 axioms. And hence we say p sub n is a vector space of polynomials of degree at most n. So as I said, I have uploaded all these detailed scenarios of how to prove that P sub n is a vector space. Now we are going to focus more on what is not a vector space, because it's very easy to prove something which is not true than proving something true. Remember, if I have to prove something true, I have to prove all the 10 axioms. It's a real hard work. So let's look at what is not a vector space. It's very easy to do. What is not a vector space? So here's one of the examples. So the question is like, is r squared a R square is a collection of all ordered pairs of the type A and B, where A and B are real numbers, and is R square, which is defined by this specific vector addition U plus V C times U, where U plus V is the normal vector addition as we have seen earlier in Rn, and C times U is a little different. So C, when C multiplied to any vector, now when I say I have a vector U in R2, that means my U is a vector which looks like U1, U2, guys. Okay, so when you multiply a scalar with it, what it happens is it multiplies only to the first element C of U1, whereas every element in C when multiplied to U2 becomes a 0. So the question is, that's how the questions will be framed in the exam, is like, is this a vector space? And you will be given how the vector space is defined. So when you look at the vector space and you say, oh, do I have to prove all of them? No. This looks like exactly what a normal vector addition of R squared would be. So this is where the whole answer is, because it's not looking like a normal. You multiply a C to any vector U, which is of this form, and it's going 0. So that's the hint. When you are looking at to prove something is not, or something, the way the question is answered, does it look familiar to us? Remember the 3-4 examples I've shown of you of specific vector spaces? If you get questions which are related to that, then you think in your mind, oh, what does that specific vector space look like? Is vector additions looking very familiar or not? Or scalar multiplication looking familiar or not? So we notice that this U plus V is exactly like R squared of our, the first example. Let me show it to you again, guys. This is, if R squared is a vector space, this is normal addition. This is the normal scalar multiplication. Because if U is a vector in Rn here, if U is a vector in Rn, what is U going to look like? This is how U looks like. U1, U2, la la la, Un. It will have n, n elements or n columns here. Or if it is, I'm looking at this form. Okay, I'm just making my life simple, as I said. So here, if I in place of n, I have an R2. So what does that mean? So if it was a normal R2, then this is where the answer is, because that shows, oh, it may not work. So now to prove something is not true, even though I'm saying is, when you start looking at this is how you make your decision. Oh, I have to let me check this one. Will it work? Okay. And the best way to prove something is not true, you just need one example. So you say let, and I'm going to make my life simple, and I'm going to pick up an example. Say let 3 and 4 be in R2. So if I multiply C, now what is the axiom? It says C times U. It is closure property. Remember, if U is a vector in R2, then C times U should also be in R2. Do you see that here? Now that is easy because it's going to be a vector, but what is the one which really works for us? Suppose if my scalar, now that's the axiom number 10. Now this one will work because if I multiply C times U, I will still get an element which is looking like an ordered pair. But there's one thing which you have to also keep in mind, and that is if 1 times U should be equal to U. This is axiom number 10, guys. A very important one for us. Axiom 10 says if you have any element U, you multiply it by 1, you should get the vector U. Okay, let's look at this one. So here I'm going to apply the axiom 10. So I say 1 times the vector 3, 4 should look like the vector U. Okay, this is what it should look like. It should look like 3, 4. Okay, this is what it should look like. 3, 4 according to axiom 10. Okay, but when we apply, so I'm going to use different markers to show the colors here. So 1 times 3, 4 should be 3, 4 according to axiom 10. But when we apply the definition given to us, the definition is C times U is only multiplied to the top. That means 1 is only multiplied to 3 and the other part becomes a 0. Oh, okay. So when we apply this definition given to us, this becomes what? 3 and 0. Now look at this one. Can 3 and 4 be equal to 0? No ways. They are not. Oh, not a star, guys. It's that this is not possible. So this one is not possible. Hence, this is not a vector space. Okay, now let's look at another example of not being a vector space. Here, M22. Now remember we have talked about this earlier, M22. It is the set of all vectors of matrices, sorry. M22 is, according to what we know from our example earlier, let me show you that. What is M22? M22 is a vector space of all matrices of size 2 by 2, and it is defined as matrix addition and matrix scalar multiplication. Keep this thing in mind. That's how, if this is true, if these things are happening, oh yes, it is a vector space. Now let's see what the question tells us. So I want you to be aware of, oh, it is M22, okay? In your mind, this should be the M22 popping up. But let's look at what the question tells us. Now here it is. Is M22 defined by a vector addition and scalar multiplication given below? Now here they are defining it to us. Is this, when I define here as given below, a vector space? Okay, let's see how they are defining it in their definition. So vector addition is A plus B, A11 plus B11, A21 plus B21, very similar. A23 plus B, A22, remember this is A22, plus B22. But the element in the second column and the first row is a 0. That gives you a clue. Oh, this is not the normal one we are used to in an M22 vector space. Okay. Alpha times any matrix A is basically alpha times A11, alpha times A12, alpha times A21, and alpha times A22, where alpha is a scalar. Oh, this is very fine. So is this a vector space? Now this gives me a question mark. Let me test it. If it is not working because of the 0, we know what is according to the normal vector space we know about as we have done earlier. This might give us the clue. So what we're going to do is first we're going to test it using a bunch of numbers, and it is the vector addition which will give us the idea. Okay, so what I'm going to do is, we know something called vector, 0 vector. Now 0 vector means what? So that's the clue. Here is something I have to test first. I know if I add A to 0, okay, that's axiom number 4. Then I should get A itself. That's what we know, okay? So let's pick up an A. So you say let A be, say 1, 2, 3, 4, okay? And I'm going to add the 0 vector to it. So A plus 0 gives me what? 1, 2, 3, 4. 0 vector here is a matrix of size 2 by 2. So according to this, I get what? It is 1 plus, so what is it? 1 plus 0, okay? And then what we notice here is 2 plus 0. So what am I getting? 1 plus 0 is 1. Notice I'm going to apply this here, okay? This is what I'm applying. 1 plus 0, then 2 plus 0 is 0. That's what happens. Do you all see that here? So I'm going to make this as a 0. And then 3 plus 0 and 4 plus 0. What we are getting? 1, 0, 3, 4. Now, is this a plus 0 the same as a? This one is not equal to a, guys. How can 1, 0, 3, 4 equals 1, 2, 3, 4? No ways. And hence, it is not a vector space. Okay. The key point is, guys, if you have to prove something is a vector space, you look at what is the non-empty set given to you. Is it familiar to what you already know about? Then you look at their vector addition and scalar multiplication, and that will be the clue for you to make a decision. Is it going to be a vector space or not? In the previous one, notice what happened was that the scalar multiple was the one which was saying, something is not right. Okay, because we know what a normal vector, r square would look like. Because this is here, the clue is this. So that means it is the multiplicative identity which gave us the answer. So the key point, what I'm saying is, if the scalar multiplication is having issues, which gives you a little question mark, apply the multiplicative identity first. Most of the time, that is the clue which will not work. Or on the other hand, if you're given a problem like this, M22, and you realize, oh, vector addition, something doesn't fit to my normal way of knowing what an M22 of the examples we know about vector spaces. So then you go ahead and apply this thing, okay? So then what you're going to do is you're going to look at the zero vector. The zero vector most of the time will not kind of work there. And that's how you make a decision. Okay, let me test this first before I do all the 10 axioms and figure it out. Oh, it's not working. Okay, be very, very vigilant, saves time. Thank you.